which is something that you will need for to implement in your last homework assignment. All right, so we were talking about creational patterns, and specifically about factory method, and so which is one of the patterns. And here is an example that we will stick to for quite a few slides. So here the idea is that we have different types of races. All right, so those are bicycle races. So we have Tour de France, which uses road bicycles, and we have cyclocross, which uses mountain bicycles, and we have a sort of like general race, which just uses a general bicycle. So that there are several dimensions here. We need to be able to have different types of races, and each race would imply a certain type of bicycle. So you see how here we clearly want something more flexible than just the code that is written here, where we essentially have code duplication, right? So byte 1, byte 2, byte 2. And the code is very similar. The only difference is the name of the actual bicycle class. So we sort of want to do better, right, than writing this create race 3 times, right? And what if we had 10 races, 10 types of races? We don't want it to write 10 times. So let's see how a factory method can help us here. Here is an implementation. So we have a create bicycle in race with some implementation, and then we have create a race that calls the create bicycle. All right, so this create bicycle is now actually a factory method, because as you can see, it is overridden in all the subclasses of race, and the create bicycle inside each type of the race, inside each race class, creates the proper type of the bicycle for that race. So create bicycle in Tour de France creates road bicycle. Note that the signature of create bicycle doesn't change. It was returning bicycle in race. It still is returning bicycle in Tour de France and cyclocross. Right? Because we want this method to be overriding. And it's not causing any problem, because if it returns a bicycle, a road bicycle is a bicycle, a mountain bicycle is a bicycle. So everything is working, should be working just fine. All right, so that's the factory method, create bicycle, and note how this dot create bicycle that we call here, it would be calling different create bicycles. It would be calling create bicycle from Tour de France or create bicycle from cyclocross, depending on the type of this object. Okay, and that's why we don't have to override create a race, right? Because it is going to work for all the subclasses of bicycle. All right, so that's how you would use it. Create an instance of a race, and then call create race, and that would call the create bicycle from the proper this object, where this would be Tour de France, cyclocross, and whatever the type of the race is. All right, so here we have an example of parallel hierarchies, where we have 2 hierarchies, a hierarchy of races and a hierarchy of bicycles. That's why it's called parallel hierarchies. Right? We have create bicycle that in each of their subclasses of race is overridden. So we see that this create bicycle, and then we follow this link here, we see that, okay, this create bicycle creates a mountain bicycle. In Tour de France, create bicycle creates a road bicycle. Right, so we have this hierarchy of races here, we have the hierarchy of bicycles here. And they are basically linked, right? So there's a dependency here, where create bicycle has a dependency on mountain bicycles, right? So that's how the proper bicycle for each type of race is guaranteed. All right, and then we have a create race, which actually calls the create bicycle. Okay, so now if you think about it, how hard or how easy would it be to add another type of bicycle in another race? Let's say we have a tricycle, right, which is another subclass of bicycle, and we have a tricycle race, which is another subtype of race. So all that would require is to override create bicycle in the tricycle race, and of course implement the tricycle class itself. So we don't need to do anything with Tour de France or cyclocross or road bicycle or mountain bicycle. So this is the open-closed principle in action. It should be open for extension, should be easy to extend, like with new tricycle race and tricycle, but does not close to modification, right? We do not need to change the create race because the implementation that we have here, it would work for any type of race, right? Provided, of course, that there are two bicycles, right? Of course, there are some assumptions, right? So here the assumption is, as you can see from this code, that in every type of race, we only have two bicycles. Okay? If we need to remove this restriction, then things will get slightly more complicated, right? But for now, the only difference between races, types of races, is the type of the bicycle. All right, and then of course our client works directly with the race, and here is just an Eclipse generated class hierarchy for that. All right, here's another example, maze game. All right, so we have a maze which consists of rooms, doors, and walls, and we have this create maze class initially that creates a maze, creates two rooms, creates a door between two rooms, adds their first room to the maze, adds the second room to the maze, and so forth, and then returns the maze. All right, looking good, but what if we need to have different types of mazes, for example?
I'm just so confused on factory methods. I'm so confused on kind of like what it is specifically. Does that make sense?
Well, specifically, a factory method is a method that creates the proper object and returns it. Like create bicycle creates a bicycle object, all right, but not just the bicycle object. It may create a road bicycle or a mountain bicycle, right? Depending on something, right? That something can be a number of things. Here, that something is depending on in which create bicycle, from which class we are actually calling, but that single line, this line doesn't change. Which create bicycle is going to be called would depend on this object. So it can be this create bicycle or this create bicycle. Right? So you see how this bike one, it may end up being a bicycle if it's not abstract. Let's see. Bicycle is not abstract, so yeah, an object may exist. So bike one can be a bicycle, or bike one, it might be a road bicycle, depending on which bicycle create bicycle returns. That's why it's called a factory method. All right, so here with a maze example, all right, we see that, yeah, it's not particularly flexible, right, because what if we did have different types of rooms? What if we have different types of mazes? This create maze does not account for it, right? So how can we do better, right? So what if we want to have enchanted rooms, enchanted doors, or some other additions to our basic room door classes? So we would have to make significant edits. A better approach would be to use factory methods. So we would have make maze, which is roughly similar to what create maze was doing earlier, right? But we also have factory methods for older objects in our game. Make room, make wall, make door. Right? So create maze, instead of now creating the specific maze object, it now calls the factory method make maze to make the proper maze, and make room to make the proper room, and make door to make the proper room, the proper door, right? The rest of the code is the same, but you see how we've changed the responsibility of create maze. So we made it a lot more flexible, so that instead of always creating a maze object or a room object, it now defers this decision to the factory method. Right? Create maze called make maze, and the make maze, in this case, it returns always the maze object. But we can see how, being a factory method, we can then override it so that it returns not just the maze in the overrated make maze, but some kind of fancy maze. Right? So here's an example. We have an enchanted maze game, which is a subtype of maze game, and we override all those factory methods so that they return more specific types of objects that we need for this particular game. So for enchanted maze game, we need make room to return an enchanted room, not just a standard room. Make wall returns an enchanted wall, and the same with doors, right? So an enchanted door between two rooms. Note how the signature is very general. It's the same signature as it was in their maze game class. For example, this make door, it still takes a room and a room. It doesn't take enchanted room and enchanted room. And we don't want it to, right? Because we want the signature to be the same. We want this make door to be substitutable for the make door that we had in their super class, right? And that's why it is very convenient to use these factory methods, because all you have to do is make sure that you are using the right game object, and if it's an enchanted maze game object, it will automatically create enchanted doors, not just the standard door, doors for you. All right, so yeah, it's the same idea as with bicycles and races. We have to override make room, make door, make maze for all the specific types of maze games. All right, so that's how we could actually implement it. So we probably cannot think of a maze game as something concrete, as a specific object of that maze game that may exist. So we only want to have specialized maze game objects. That's why we make this maze game class abstract, and that allows us to make their create room, create wall, create door object methods abstract, so that we defer their implementation to the specific enchanted maze game and whatever other maze game subtypes we might want to create in the future. Right. The fact that there is no implementation for these methods, create room, create wall, create door, does not mean that we are not allowed to call them. So here, see how create maze is not abstract. So we provide implementation, and in this implementation of create maze, we call create room, create wall, create door. So the question might be, well, how is that at all possible if there are no implementations to create room, wall, and door? What are we calling here then? And the answer is, this call to, let's say, create room is not to call the implementation of create room from maze game, because there's none. But it's a promise that whatever object we might have in reality, it wouldn't be a maze game, because maze game is abstract. It would be one of the subtypes of maze game. And since create room is declared as an abstract method in maze game, then every concrete subclass of maze game must have an implementation of create room. So when this create room is called here, it will be the create room from that specific object that is a subtype, that is an instance of a subtype of maze game. Right? When we don't use the dot notation here, implicitly it's the same as saying this dot. Right? So this dot create room, this dot create wall. So this would refer to the actual object, and actual objects will have create room implementations, because otherwise they wouldn't exist, right? An object can only be created from a concrete class, and a concrete class will force you to have no abstract methods, right? You cannot have abstract methods in a concrete class. right? Because otherwise that would inhibit the creation of objects, all right? And so here are more examples. Enchanted maze game overrides create room, create wall, create door, and it makes sure that it creates all those objects, room, wall, door, that are specific to this type of the game. Right? We might have another type of maze game, maze game, and that one also overrides create room, wall, and door. Right? And you can come up with more types of maze games. And again, note how this this arrangement of code, this structuring the code this way makes it easy for us to extend. Right? If we need to add yet another maze game, what do we have to do? Just declare that class whatever maze game extends maze game and override create room, create wall, create door. Right? No existing classes would be affected. So open for extension, closed for modification. All right, so we've looked at the bicycle example, maze example for the factory method. Right? So this is one of the design patterns that were in their original Gango 4 book. All right, and the reason it's called the factory method because it's just one method. We can always identify it. We can say, well, create room is a factory method, right? Create wall is a factory method. Create bicycle is a factory method, right? So apart from factory methods, yes.
What's the difference between a factory method and a producer?
Well, a producer is any method that returns another object. Okay, it doesn't have to be a factory, right? So, for example, in your homework you had add method that was adding two polynomials, this and another polynomial, and it was returning the resultant polynomial. Right? It is a producer, but it's not a factory method because you cannot ask it to just create a brand new object of, let's say, a subtype of polynomial. Right? So every factory method is a producer, but not every producer is a factory method. All right, so factory object, also known as abstract factory. These are two names for the same patterns and for the same pattern. In some literature, you see it called factory object. In some other sources, it's going to be called abstract factory. Please know both names, right? Because we may refer to this design pattern by either of the names. All right. So the idea here is that instead of making the job of creating an object the responsibility of a method, a factory method, we say in this pattern it's going to be delegated, it's going to be the responsibility of a factory object. So we're going to have an object that is responsible for creating other objects. And of course, this object would be working through its methods, right? So it's sometimes challenging to distinguish between the factory object and the factory method. The main thing to look out for would be in the factory object pattern, right? We have this abstract factory, so there's a class that delegates the responsibility of creating an object via composition, right? In factory method, we just use inheritance, overriding their factory method in subclasses to make sure that their overriding factory method creates the correct type of the object. So let's look at some examples, and hopefully the difference between factory object and factory method leads to related design patterns is going to become more evident. All right, so instead of, remember previously we had a create bicycle method. So instead of having that single method, we now want to have an entire class which would be a factory of bicycles. Okay, so we call it appropriately bicycle factory, and this class has factory methods to create a bicycle, frames, wheels, and so forth. Right? And then, of course, we want to have the ability to use those factory methods. That's why we have to override them, right? No matter how you slice it, right? If create bicycle is a factory method, it has to be overridden. But now you see that it's overridden not as part of their bicycle hierarchy, but as part of the bicycle factory hierarchy. So we separate their job of creating those objects from their hierarchy of classes that were defining the object. Previously, we had the bicycle hierarchy, bicycle, road bicycle, mountain bicycle, and we have create bicycle factory methods sort of embedded there. Now we want a clearer separation of what the object itself is, bicycle with whatever properties that it has, and something that helps us create those bicycles. That's why we sort of move their factory methods into a separate class. And we call it the factory. And now when we extend this base factory class, bicycle factory, we create specific factories for the road bicycle factory, for mountain bicycle factory. And in these subclasses, we override the factory methods like create bicycle or create bicycle in mountain bicycle factory. Right? So this little restructuring, right, leads to the pattern that we are doing now being different from their factory method. Right? We have an abstract factory, or we have a factory object. All right, so how would that basically connect to the rest of their hierarchy, in particular their race hierarchies? It's going to be just one little modification, right? For a race to now be able to create the proper bicycles, it needs to have a bicycle factory object. So in the constructor of race, we have a B factory, new bicycle factory. B factory is now a field of race. So that's what we mean when we say that a factory is embedded in their line of the factory through composition. See how here we say via composition, right? So here this is via composition. B factory is now a field in race, and that means that B factory is a field in any subclass of race. Okay, so we just need to make sure that the constructor of each specific type of race creates the proper factory, because it is the type of the factory that will be determining which type of bicycles that this factory is going to be producing. Right? So if we here write our own bicycle factory, it means that, all right, so this B factory will be producing road bicycles when we call create bicycle. Right? If here we wrote instead of road bicycle factory, mountain bicycle factory, we would be requiring Tour de France to use this B factory that would be producing mountain bicycles for us. Right? So it's important to get the proper type of bicycle, the proper type of factory object created. Right? But other than that, create race method is inherited by all the subclasses of race, so no changes are required here. This code works. It creates a bicycle from a factory. If the factory is the right type, that's all it takes. It is guaranteed to create the correct type of bicycle. So, then we don't see the actual the actual creation of bicycles here, because it happens here in the base class in race. So when, for example, you have an object, Tour de France, and you look at bike 1, its compile time type would still be bicycle, right? But its runtime type would be road bicycle factor. Of course, we assuming that those are not just local variables like they are here, but they are actual bikes that are stored as fields in their in the object, right? So here probably would be better to have bicycle bike 1, bicycle bike 2 as as fields here, not just as local variables. All right, and this is the hierarchy that we just reviewed with the Eclipse UML notation, right? So note again, we still have the parallel hierarchies, the hierarchy of bicycles right here, the hierarchy of races, right? But we also have a hierarchy of factories now, right? So here's the bicycle factory, here's the road bicycle and mountain bicycle factory. Note that this edge here, right? Note, it's not this triangle. It's not. It's a different type of arrow, right? Because bicycle factory is not inherited from race, of course. Bicycle factory is being used by race. So bicycle factory is inside of race. Race includes bicycle factory through composition. Right, so that's the example of their usage of this bicycle factory, right? So here we have their constructor, and we create, when we are creating a race, we are creating bicycles, like just call them the B factory. All right, so now with all the other types of bikes, we just have to have each type of a bike will have its own factory, a road bike factory, mountain bike factory. Right? And here we can take it further to say, well, when we are creating a bicycle, we might be actually assembling the bicycle from its components, from frame, wheels, and so forth. All right, so that's that, note how this up to this point, right, up to here, which bicycle type is used for each race is kind of hard-coded here, because each type of the race will have the dependency on their type of bicycle. So Tour de France is always going to be using road bikes because it instantiates a road bike factory which only knows how to produce road bikes. If we want to have less, if we want to have more flexibility, if we want the system to be less rigid, we're going to say, well, would that be possible for me when I'm creating a Tour de France race to actually specify which type of bicycles I want this race to have? And the answer is yes. It's not actually that hard. All it takes is to add a parameter to the constructor, so that the constructor takes an instance of their bike factory. So instead of creating the factory here, the constructor may actually assume their external code to create the factory, and then just pass the factory to the constructor, so that the constructor creates the bicycles that would correspond to the type of their factory that they perceive. And here is exactly this example. See how now a race has a constructor, B factory, and it takes this external B factory, right, external bike factory, and it stores it as one of the fields. So whenever the need arises to create a bicycle, it calls this B factory to create a bicycle. So what this B factory is now not known until the client decides to instantiate a race. Right? Now the client will be responsible for creating a bicycle factory, right? And it has to do so before it instantiates a race, right? Because there's no longer a rigid connection between the type of the race and the type of bicycle, right? You can do mix and match, right? You can do any race with any type of bicycle, just create the proper B factory and bike factory, pass it to the constructor of the race. All right, so here's an example. Yeah, we can make Tour de France use tricycles, right? If we pass tricycle factory to the constructor of Tour de France, right? So that is, and of course, there are all other combinations possible. All right, so with this slight modification, this is what our class diagram is going to look like, and I'll just summarize with the create bicycle, right? It is still a factory method, but it's not just a factory method designed better, because we clearly see that there's a hierarchy of factories: bicycle factory, road bicycle factory, mountain bicycle factory. Right? So create race, it calls their factory method create bicycle, but it relies on their factory object that is stored as a field inside of their race. The proper type of the bicycle to create will still be guaranteed by their overridden create bicycle, but now create bicycle is not in the bike hierarchy, but it's in their bicycle factory hierarchy. All right, so that's that, and yeah, there is an extended example that I encourage you to review, but we're just going to skip it for now. Right, it's a soup factory, right? So it's a little larger, as you can see. So I believe it as an exercise. All right, so factories are very common. Factors are also used in the standard Java library, in the JDK. Right, so here's an example. We have a date format class, which basically encapsulates our ideas about how that date should be formatted. Right, just date or time or date plus time, and then in all the different languages. Right, so we have a get date instance method of date format that returns a date format object. Okay, so it's not a date format object, it's actually one of the instances of their subclasses of date format. Okay, so essentially the date format object that we get from get date instance would correspond to their factory object. And then when we call methods of that factory object, we would be getting different types of formatters. Right? So there's a get time, get date instance, a date formatter, so that shows just a date, or get time instance, just a time, or get date instance with the specified locale, right? Which incorporates the language and all their cultural assumptions about how the date should be written. Right, so now we have three different date format objects. Well, again, do not be fooled by the fact that all these three variables are declared as date format. Okay, they're not going to have the same object, right? So get date instance is going to return an instance of a subclass of date format that would be specific to formatting dates, usually just the date. Right, so df1, df2, df3, they have the same compile time type, but they are going to have different runtime types, right? Because they all going to have different objects, even by type, right? Not just different objects, distinct objects, but different objects by type. All right, and that allows us to have very elegant code. So we have a date object which corresponds to today. And then we similarly call the same method format, but on different variables. And the results are very different because you are actually not calling the same format method, right? Do not believe your own eyes, right? They are different format methods because the format method is overridden in each of their class that extends date format, right? So we are here dealing with three different classes that extend date format, and they override format so that whenever we call format, the proper overridden version is selected depending on the runtime type of df1, 2, and 3, so that it either prints just the date, July 4th, or prints just the time, or prints the date, but with the proper locale, country, and so forth. Okay, so this is another example of a factory, abstract factory, right? A factory object. All right, what else we could do? We could replace factory class with a supplier and function method that supplies an object. Right, so our bicycle can now be turned into an interface, and with a get bike method that serves as a factory method. And then we can have subtypes of bicycle where get bike is overridden, right? And then we could have the mountain bike factory as a new class that overrides. Here, right? So overrides the the mountain bike factory by type is the supplier of a bicycle. Right? So the supplier is just a class that is defined in JDK. It is generic, so it takes an argument, the type argument bicycle, and then it takes a lambda function that determines which factory is going to be created. Right? So mountain bicycle is simple. So this is the notation of a lambda function, an anonymous function that takes nothing and returns a new mountain bicycle. Right, so yeah, you don't have to use lambda functions, but they're convenient here. All right, so now if you want to have even more flexibility, we can go for dependency injection. So let's look at our last implementation here, and it was pretty flexible. So we no longer had this rigid connection between the type of the race and the type of the bicycle. Right, so we could mix and match, but we had to make the decision at the time we were writing the code. Okay? So we would have to say, well, to the France, we have to create a bicycle factory object to pass to the constructor of the specific race object. Right? What if we want to defer this decision, right, which bicycles Tour de France is going to be using even further, even to the runtime? And this is exactly what can be done with dependency injection. So the idea here is that we can store this connection between the type of the race and the type of the bicycle it uses in, for example, a text file. And then that text file can be read at runtime. And using Java reflection mechanism, we would restore from the text file, we would restore the name of the class, and then we would instantiate that class at runtime. So at compile time, there would be absolutely no knowledge of which bicycle goes with which race. So let's look at an implementation. Here we are reading this bike factory file, and the file, there is an example called injection demo. Let's actually run it. I know we don't have much time, but otherwise I think it would be kind of hard to digest the dependency injection. Let's hope Eclipse loads quickly. Come on, Eclipse. I know you're written in Java, but still. Fine. All right, injection demo. All right. So this is full working code. All right, so what do we have? We have a hierarchy of bicycles, nothing particularly new here, right? So just constructors, no factory methods here. We have a bicycle factory, all right, so which tells us that we have a factory object or abstract factory pattern here, right? See how a create bicycle, all right, it is going to, of course, create road bicycles. If it's in the road bicycle factory, create bicycle. In mountain bicycle factory, creates mountain bicycles. So where is the connection between their race and their bicycle, the type of bicycles? Well, we still rely on the factory. That's why the factory, the bicycle factory, is in race composition. So race has a bicycle factory. And we still rely on the constructor knowing their object for their bicycle factory. So again, that's not something new. This is our create race implementation as it was before. But the difference is going to be in their code external to our bicycle race, bicycle factory hierarchy. The code that will be deciding which factory to create to pass to our constructor here. Right? So see how this is solved in this case. So we read this bike factory data file. Right? It's just a text file. So let's. Right? So note how its name is the name of the class, but fully qualified with the name of the package. Note that the package is injection, so the fully qualified name of any class would be the name of the package. Injection dot is the name of the class itself. Then we read this injection dot road bicycle factory, and we are creating a factory class, which is a meta class. Right? It's a class of classes. It's a class that represents the entire class. So basically, this for_name method takes the name of their class as text, as a string, and creates a class that represents this class. Okay? I know it's a lot of class that represents a class. It's a mouthful, right? But hopefully you get the idea. So this factory class will be an object in Java that represents the entire class whose name we just read from the file, road bicycle factory in this example. And then we are able to create a new instance. Once we have the class that represents road bicycle factory, we are able to create an instance, and this is our B factory. And from this point on, everything else is the same as without dependency injection. Right? We pass this B factory to the race, and here we are. Right? So what happens is when we run this as is, right? It's going to be reading road bicycle factory from this file, and that's why it creates road bicycles, right? If we now change this to what do we have? How's it spelled? Mountain bicycle factory, right? Then the same code would work differently. It would create mountain bicycles for our device. So you see how the dependency is completely external, and it's injected into our code at runtime. Right? And here my example is set up so that I had to kind of restart it, run it 2 times to show the difference. But in reality, right, you could have had the exact same code. Let me show it. So here we would have this, and then I know it's not very elegant, but in any case, right? If here we would repeat the same code without rerunning, without recompiling, without rerunning, and the contents of byte factory is different, we will see that the same code that creates a new Tour de France would create a new Tour de France with a different type of a bicycle. You had a question?
Yeah. So it's basically how the injection thing is working is that well, not injection, I mean like the class 4 name was that it was just reading in a bicycle, it was reading in the name of the, and you said this before, but I just want to double check. You're basically reading in this file, this name in this file, and it creates a class. But in order to create that class properly, it then draws on an existing class.
Well, the thing is, with a new operation, you cannot create a class whose name you don't know at compile time. Using Java reflection allows you to overcome this limitation. So if you don't know the name of the class that you want to create at compile time, but you do know it at runtime, for example, by reading this name from the text file, then you can, through Java reflection, can create an instance of this class. Right, so this factory contains the string, right, and obviously we cannot use the name, the proper class as the object from just the name, right? That's why we have to sort of bootstrap it, first turn it into a meta class object, and then use that meta class to create a new instance of whatever that meta class represents. All right, those were some of the creational patterns, right? So the factory method and the factory object, also known as abstract factory. All right, so they help us overcome some limitations of the new operation, which you can only create the same object without any flexibility. Factory objects, as you can see, factory pattern allows us to create objects of different types. All right, so prototype pattern is another creational pattern. It's a pattern which allows the object to create itself. So basically, object itself is a factory that is capable of producing clones of itself. Right? So each class can define a clone method that would return a copy of their object on which this clone method is invoked. Right? So if we have a class bicycle, we can have clone method in the bicycle that returns a bicycle. Unfortunately, just providing a clone method is not sufficient, right? Things are a little complicated. So we have a clone method implemented in object class. All right, so it is implemented like that, protected object clone. So it returns an object, which means that we can actually override it in any subclass of object, and we don't have to stick to object. We can replace the return type with any subtype. So, for example, returning bicycle is completely valid. All right, the thing is, their cloning will take their current state of the object and create its exact copy. Unfortunately, the fact that a clone was implemented at the level of our super cosmic object class, it was not. Turns out it wasn't particularly an excellent idea, because then it means that all classes will have this clone method, even if they don't provide one thing and inherit it from object. But not all classes are ready for cloning, right? The implementation of clone in an object can only do some very basic stuff. It doesn't know about any of their fields that might exist in their subclasses of object, right? So it's very limited, which means that realistically, if you want any of your classes to implement cloning, you sort of have to override this code. right? But as with any inheritance, you're not forced to override that language, right? That creates this problem, right? If we don't override clone, it's not going to work correctly, and nothing forces us to override it. So they came up with a not very elegant solution that actually does not treat any class as clonable unless it specifically implements a clonable interface. All right, so that's why things are getting messy. Right, so there is this interface called clonable that any class that wants to support cloning has to declare that it implements it. And if the class does not implement it, it will still have a clone method, but an attempt to call that clone method would result in an exception called clone not supported exception. Right? It's very hard to believe. Right? There is a clone method, but if you call it, you're going to get clone not supported exception. Right? Unless you implement their specified interface and override clone. All right. So why is it so complicated? Because at the level of their object class, the only meaningful implementation of cloning would be just field by field copy, which, as we know, is called shallow copying. And it's going to present a problem if we expect that a truly independent copy is created, right? Which we know in case of calling clone from the object class is not going to happen, right? So it's like you have a child, right, and you think of them as your clone, right? But they share the same house with you, right? So they're not completely independent, right? So if you want your clone, you want them to have their own car, their own their own house and everything on their own. That would be a truly independent clone, right? That has its separate life. If you share some resources with them, they're not a deep copy of you, right? So that's a major problem, and so that's why they had to come up with this not very elegant solution. By saying that a class that wants to support cloning has to do the following: implement clonable interface, override clone method that inherited from their object class, and that's it. And if you are still not surprised enough by Java, you might think, well, clonable interface, what methods does it provide, right? So if I implement clonable interface, am I under obligation to override clone or to provide an implementation of a clone? And the answer is no. Clonable is actually an empty interface, so it's a so-called tagging interface. It's essentially, it is really empty. It's like interface clonable and then just braces. Right? So it means that it's very easy to implement clonable formally because you don't even have to provide any methods. Right? Clonable interface does not have any methods because the clone method that you really should override is not coming from your obligation to implement a method from clonable interface. It comes from their understanding that their implementation of clone that you inherited from object is not going to work correctly, and you should really should override it. All right, and this clonable interface is just used to help the compiler see which classes declare that they support cloning versus all the other classes, because we know that all classes will have the clone method. Right? So the compiler cannot say which really supports cloning, which is not, which is looking at the methods. Right? Because all classes will have the clone method. That's why they had to come up with this additional tagging interface clonable. All right, so that's a sad story, right? This is their exception. So if your class does not properly override clone and does not implement clonable interface, when someone calls clone on an object of your class, they're going to see this clone not supported exception.
So if you had a class that then you had a generic class where you wanted to have the input types be the parameter types be be clonable, you have to say like the class such and such, and then in the brackets like t extends clonable. Would I say clonable bracket t?
Well, first off, you cannot say extends clonable because clonable is an interface. You have to say implements clonable.
In the braces?
No, it's with the generics, things are even more complicated because you cannot have you cannot create instances of generic classes. Right? You cannot if your type parameter is e, you cannot say new e, right? Because as we discussed, all type parameter information is erased. So at runtime, you don't know what that e type is other than that it's an object or the bound. You implement an interface. Well, because if you just override clone method, the compiler doesn't really know about it. Right? So you have to explicitly say that not only do I override clone, I say that I override clone by implementing this empty clonable interface. Yeah?
Is there usage of clone if you already have like a copy constructor?
Well, there's no such thing as a copying constructor in Java. Right? The only thing you get is an empty compiler, an empty constructor if you don't provide your own. So you can implement cloning through a separate method, right? But you cannot create a copy. There's like no as such there is no copying constructor in Java.
If all the clone method does is throw exceptions, why does it exist in the first place?
Well, no. The thing is, it only throws an exception if it sees that your class does not implement clonable. Okay? So the implementation of clone, it actually works. Okay? So if you are happy with it, you still need to override it. But in your overridden version of clone, you can just call super.clone. Okay? And you're going to get the exact implementation of clone from object class. Right? But they force you to do this so that you do this consciously. Right? Not just, oh, I inherited clone, let's use it. Right? But override clone, and if you strongly believe that implementation of clone works for your class, then call super.clone and be happy. Right? Because more often than not, it's not what you need because it's just shallow copy. All right, that's the prototype pattern and how it's implemented in Java in a little ugly way. Right, so we have shape with clone. We have all the subclasses, circle, rectangle, square with the clone. All right, see how if we want our shapes to be clonable, right? For the client to be able to call clone on a shape to create a copy, identical copy of a shape, we have to first say that this class shape implements clonable, and then provide override clone that is inherited. Okay, so this is the right. So see how we call super.clone here, right? And then we just catch a clone non-supported exception. Right? So basically saying, hey, did it work? Did it not? If it worked, right, then we return the clone. Okay, so that's and the client would look like this. All right, so we have for example, want to create a clone of an object that we place in a hash table in this case. Right, so we have a hash table, and if you want to get something from the hash table, right, we get the cached object, cached shape, but instead of returning the shape, we want to return a copy. Why? Well, remember, right, hash table, we should not allow anyone to change the objects that are in stored there, right? Because again, that would be a rep exposure in most cases. So we want to return a copy of the object that we just extracted from the hash table. So that's why we call clone on it. All right, and that's the driver code for this example, right? So we get the shape from our cache, and then we can actually look at the type. It's going to be not shape; it's going to be a specific type, like circle or rectangle, and it's not going to be the same object that is stored in our hash table. All right, what about our bicycle example? What if we want to be able to create to use their prototypes here? Well, we can change the way our bicycles are created by saying, instead of using a factory method that we ask to create a certain type of a bicycle, we can actually take a bicycle object to serve as an example, and then create prototypes, right? Create clones of that object, right? So here's our prototype. We just store it, we don't do anything with it. But in create trace, we use this prototype to create clones of it. Okay, so for us, this prototype is sort of read-only. This is our, this is our sample. And whenever we need to create more bytes, we just upload that sample. Okay, so that would be an example of using the prototypes for this bicycle example. Right? So how would we specify the race of the bicycle? We would create an instance of the bicycle and pass it to the constructor of Tour de France. The race would not do anything with this object, so that's how we avoid rep exposure, right? Because even if this class tricycle is mutable, right? The race class doesn't actually do anything. It doesn't take anything from it except for it creates clones. Okay. All right. So are clones confusing and dangerous? Sure thing. All right. So first, we know that clone that we inherit from object, it is shallow. It just copies field by field. Right? If fields are references, it means that the corresponding objects are not recursively cloned, but just references are copied, and that makes the original and the clone to share the state. Right? So that's, of course, is dangerous, right? Because we are creating multiple aliases that point to the same object. So in order to avoid all the problems that can result from sharing state across multiple objects, make a deep copy. Right? Making deep copy, as we discussed, may be a non-trivial task, and that's why clone in object doesn't really do this. Right? So if you want deep copying, it's your problem. You have to think how to implement it and avoid all the problems like cyclical references or poor performance if your object is very large. All right, so next group of design patterns is called sharing design patterns. Well, they're kind of creational patterns as well, but they are very different from the prototype or the factory subgroups of the creational patterns. So here, the idea is that we want to control the process of creation of objects in a way that maybe if you already have a suitable object, we want to sort of cancel the creation and just get the existing object that we already have. Okay, so there are two patterns that fall into this group. And if we have time, we will look at more sort of examples of design patterns that are related to these two. Right? But for now, let's start with two, singleton and interning. Singleton is a pattern that ensures that only one object ever exists. Well, only one instance of a particular class, not one object, globally, but only one instance of this singleton class. Right? So that means that if we need an object, we don't need to create it. right? It should be already there. Interning is a very similar concept, but saying, well, we can have more than one object, but only one object per given abstract value. And a good example here would be true and false for Boolean objects, right? So it doesn't make sense to have multiple true objects or multiple false objects because they're going to be the same. They are immutable, right? So we want to limit the number of objects of the Boolean type, right? We are talking about, of course, the boxed type, right? Not the primitive Boolean, right? But the boxed Boolean, right? We only ever want to have two objects, one that corresponds to true, another one that corresponds to false. And an attempt to create a new true object should be intercepted, and instead we should be given an existing true object. Because they are immutable, it's guaranteed to be the true object that we need. All right, so that's the general idea. Let's look at how their implementation goes. All right, so what if we want to have only a single object of bank, right? So what we're going to do is first we disable the ability for any external code to call new on bank. And we do that by making the constructor private. So since a constructor has a private access modifier now, it means that no other code would be able to call new. Right? Only code from within this class. All right. And then we have an instance field that would hold a reference to this single object, single instance of bank class. So we provide a get instance method to our users, to our clients. It's public. And what this method does, it checks whether the instance has already been created. If not, then this instance field is going to be null. And then we create this new and only bank instance. And we store it in instance. If instance is not null, we return the instance. Right? So basically, no matter how many times someone calls get instance, it's not going to lead to the creation of more than one bank object. And since no one is able to create bank instances directly, that guarantees that at most one object of type bank is ever going to be created. That can be null, that can be zero, right? That can be none. If get instance was never called, right? But there can never be more than one bank object, right? So this is the diagram of this example, right? And this is the corresponding code. Note how we have a private constructor which is empty. Why did we have to do this weird thing? We know that we are given a constructor that has no parameters, that has no implementation, right? So essentially, we are given this constructor by the language automatically. Why did we have to essentially do this over again? The important thing to remember is that the default constructor, which has no body and no parameters, is public. Okay? So if you remove this line, it's not going to be a singleton pattern anymore because anyone would be able to create new instances. So we have to make the constructor private. We have to provide the constructor so that it replaces their default constructor that we would otherwise get. Right? And then we just call get instance, right? Which, as you can see, returns an instance. So here is the driver code. All right? So we create a new single object, and then we call get instance on that single object to get that single object that is ever available. Right? Note how this example is slightly different from the previous one. In the previous one, we could have no instances or one instance. Never more than one, but it was possible for us to have no instances, right? If no one ever called get instance, right? Because this instance is a field which is initialized to null when their bank class is loaded by their JVM. In this example, an instance is created when the class single object is loaded. So we cannot have a case where no instances of single object exist. no instances exist, right? We always have one instance because it is created when the single object class is loaded by the JVM. So all this get instance method does, it returns that instance, right? That instance always exists. All right, so that's that, and yeah, we cannot create a new single object here, right? It's commented out because if you try to compile it, it would be compile time error. We cannot invoke a private constructor from their code outside of single object. All right, so here is another singleton example. This time with their modeling their source of a database. So see how we here make the constructor private right here, and then we provide a get instance method that returns an instance. Right, that instance is the field that is always initialized with a new object. So again, it has to be a class field, so that there is only one field for the entire class. Right? So that's why it has to have static. All right, interning pattern is not one of the original Gang of 4 book design patterns, but it is widely spread. So we need to definitely talk about it. Right? So again, you can think of it as an extension of. You can think of it as an extension of the singleton pattern. Singleton, at most one object exists. Interning, a small number of objects may exist. And what the small number is, it varies. A small number can be 2, or a small number can be 256. Right? So if you've if you were ever wondering about like Python, for example, Python interns small integer values from -128 to 127, right? No matter how many times you say 116, it's going to be the same object, right? But if you go over 128, right, then you might have multiple objects that have 10,000. Okay, so this is due to interning. So in case of Python, the interning pattern for integers says there are 256 objects that may exist, right? One for each abstract value, one for each integer in this range, -128 to 127. All right, so the idea, why interning pattern? Because we don't want to create duplicate objects. Okay, so obviously this only works for immutable objects, right? If objects are mutable, right, they can change. We should not be implementing this pattern. All right, so let's skip this example and basically turn into a slightly different example. Right, so here we have a hash map, right, of string and string, and we are checking if our hash map contains a key given by this variable n, and we return that object right, by key n from the hash map. Right? If it's not there, we put n in our hash map. Right? So since n is a string, right? So if strings were not interned, that would create a problem. Right? Why? Because imagine we are trying to add, and there is no add method here, but you can clearly imagine that, right? We can just get a canonical name for string hello. Right? Hello is not in our hash map, so we're going to put hello as the key and value in our hash map. And we return n, hello. Okay, sounds good. So next time someone comes in with a string hello and asks if it is in the hash map. It's going to be a different object of type hello, and Therefore, it's not going to be, right, if we check contains key, if equals is not properly overridden, it would say it's not contained in the hash map. And you see that would create a problem. Okay? So interning helps us here with immutable types, saying that, well, if we are attempting to come in with the same string hello, it's guaranteed to be the same object that any other string hello. And that's why it would be contained in the list of keys of our hash map, and we would use that key to extract the string that we need. All right, so that's one of the uses of the interning pattern. All right, so Java strings can be interned. In this example, we played a lot in the beginning of this course, right? So we know that anything that is a string literal, so these two cats they're going to be the same object, right? So strings are interned in Java. But if we create a new object with a new, it's going to be a different object. It's going to have the same state, the same value, but it's going to be a different object. So B and C, A and C are not the same object, so this prints false, but they have the same value. So if we call equals, it prints true. All right, so this is just the documentation for intern, so here is actually how Booleans are implemented in Java in the standard library. So it is interning, right? So see how we have two objects that are created initially, true and false. And whenever you come with a Boolean value, right, you're not going to get a new object. You're going to get either a true object or a false object, one of the two existing objects. Right, so this is the boxed Boolean, of course, right? So not the limited Boolean. All right, so that's their implementation of interning for Booleans in the standard Java library. Does anyone see a problem here with this implementation? Yeah, it's actually flawed. It's actually broken because what they forgot to replace this public with private. So they left the constructor accessible, which defies the whole purpose, which kind of kills the entire pattern. Right? So anyone can do new Boolean and create a new object for true and false. So they failed to implement interning. Right? That was like a big oops. You know, the worst case, the worst thing is that there's absolutely nothing that can be done once this code is out there. Right? It cannot be changed. Right? It's too late to try to say, hey, in the next patch we're going to change this to private, because then it would break the existing code that calls new on Boolean, right? And we don't want to break the existing code. And there's no other way of fixing it. So they basically just gave up. They admitted, you know, that they messed up, and yeah. So that's you know, that's the end of this, you know, sad story, right? So yeah, they say they tag this constructor as deprecated, meaning that they will probably, you know, at some point in the future, actually remove it or make it private, right? But they haven't done it. You know, now we are in Java 19. This constructor is still there, right? Because they're still afraid to break some old code that calls this constructor. Okay, so yeah, that's, you know, see how, you know, how you can mess up royally by just, you know, forgetting one little tiny keyword here, and there's no elegant way of fixing it. Right, so, and of course, you know, one of their lead designer, Joshua Block, by the way, he wrote a pretty decent book on Java. So, You know, they basically say, well, yeah, don't use it, please, all right? But yeah, you know, Boolean type should not have had public constructors. Just don't use it, and that's it, right? So, really, no good fix to this. All right, so that was part one, and let's switch gears and talk about some other patterns. All right, so the observer pattern, right? So this pattern is designed around the idea that we have data, which is called a model, right? Which is something that that contains, for example, for your graph, right? That would be your nodes and edges, right? So that would be your model. And we have observers. Those are classes that are interested in consuming your data with their intent to present this data to users. So they are called views. And for the same model, we can have multiple views. For example, your graph data, you can just print it on the terminal, right, as an adjacency list. Right? That's one way to view your graph. Or you can have a view where you use some fancy JavaScript library, D3D or whatever, to visualize this graph as an actual graph, right, with circles and arrows. Right? The model doesn't change, but there might be multiple views for the same model. And the idea behind the observer pattern is that it should be easy. The model should be separated from the views so that we can easily switch views, or we can easily provide multiple views without affecting our data, our model. Right, so here's an example. Client stores data in data class, in a data object, right here. And this data can be viewed as a plot, bar chart view, or as a spreadsheet view. Right, so the problem with this approach is that, if we need to add a view or change a view, or do something with a view, we must change the data, right? Because this arrow shows that there is a dependency. Data knows about the spreadsheet view, data knows about the bar chart view. So if we have to add another view, we have to modify data, our model. And this is something that we don't really want to do. That goes against our open-close principle, right? If we just need to add another view, we ideally want to add this view as a class and not even touch data. All right, so let's see how the observer pattern helps us achieve this goal. This is, remember, solid, the abbreviation, right? Where L is list of substitution principle, right? And S is a single responsibility principle, right? This SOLID acronym. Right, so single responsibility principle. The view should only be responsible for displaying data. It shouldn't be storing data. It shouldn't be keeping anything inside of it. Right, it's just visualization. It's just the presentation. Right, so here's what would be a better design that would minimize their interactions between their data, the model, and views. Right, so we would have their update views in our naive initial design that would update, right, if data changes. This is how data, our model, would inform the views of the change. Right? So for example, we received a new data point. Our graph got a new node. Right? So it needs to let the views know so that views can, visualize this new node. Right? So in the naive design, we do this by calling update on each of their views and sending them new data. In a better design, we may employ an approach that is based on callbacks. A callback is a method that we designate specifically to be called when something happens. Right? So basically, like we say, if this happens, call us back. So the way it is implemented with their observer design pattern is their model maintains a list of observers. An observer is an object that is interested in being notified when something in the data changes. Right? So imagine this list is filled with all the observers, so when something actually happens, right, all we have to do in our model is to go over all observers and call update on all of them. See how in this better approach, it is very easy to add and delete observers, right? We don't care what observers are. If we add a new type of an observer, a new type of the view, that would not change this code in data. Okay? So all observers, they are similar in the sense that they implement the same interface observer, which calls for an update method. Right? So that's what their class diagram would look like for the observer pattern. Like see how we have attach and detach. These are two methods that allow us to either add an observer to the list of observers or remove an observer from a list of observers. And this is the list of observers. How this observers relates to data through composition. Observers, right? Data has observers, and our simple data, our simple model, one has multiple star observers. Okay, so when data changes, it will notify observers by going over all of them and calling update. So method update is prescribed by their interface observer, and each specific observer, each specific view, will have its own implementation of update, right? Because of course, these views are very different. One is spreadsheet, another one is bar chart. All right, so that's how it would be happening when we create a new instance of our model, and then we want to attach a view, attach an observer to our model. So model internally will keep a list of all observers, right? All those who are interested in being notified when data changes. So it looks pretty decent, but we can do even better, right? So let's see what their improvements here are. Right? So observers, an observable maintains a list of observers right here. Right? Attach, detach are used to modify this observers list. And now we can make data and we can make data a subclass of observer. Okay? So see how this is observable. It probably should be an interface, right? Or an after class. And how data is now implementing or extending depending on whether it's an interface or an after class, the observable. So doing this guarantees that our model is going to have attach, detach, and to notify observers, right? So the difference is here data is just a standalone class extending object. Here data extends observable. All right, so that would be their observer pattern, right? So just with more observers added, slightly different example, binary observer, octal observer, hex observer, and this is if we want to represent the same number as either in binary or octal or hexadecimal. Okay? So the same thing, but having different, right? The same integer, but with different ways to visualize it. All right, and here is an example of code. See how attach just adds an observer to the list of observers, and then when something changes, right? So notify all observers is called from set state. So set state changes the state of the data. Data is just an integer, right? For this binary, hex, octal, and when this integer changes, right, it can only change through the set state, right? Because this state field is private. So the only way for someone to change the integer in our model is by calling set state. And when that state changes, automatically we make notify all observers call, and notify all observers goes over all observers and calls an update on them. Okay? So now that if we have a binary observer, we just attach it to our data model. Right? If we have a hex observer, we attach it to their same data model. So we have one data model and 3 different observers. So when our data changes, all 3 observers will be guaranteed that their method update is called, and they will visualize this change of data appropriately as a binary, hexadecimal, or octal. All right, so that's the example output, and now with this observer model that we just reviewed, right? Let's look at the update method. Right? So what does it do? Well, it pushes the new state of data to the observers. Right? So we can look at this example here. Right? So whenever we have new data, it is sent to all their views. Right? So we are basically sending the update to the observers. Or we could use a different approach. Here, when update happens, the view reaches out to the model. Note how each view, each observer here, has subject, right? And subject is our model. And it can reach out to the subject, to the model, and say, well, give me the current state. I know something has changed. I don't have this most current state, but I want to reach out to the model and grab it. Right? So clearly, we see 2 different patterns. One is called the push model, another one is called the pull model. So push model is when the object sends the information to observers, right? So pushes the information to all the views, right? That was our first example. And pull model is when their object just notifies the observers that something has changed, and their observers pull the new data from the model. And both models are possible with an observer pattern, right? So it basically boils down to how this update method, how we want it to work, right? If we do this, update this, we are sending, what is this? This is an instance of the model, right? Because this is inside notify observers, and this is part of data class. So we push the update to the observers, right? So yes, no. We see that in fact it's not a push model; it's a pull model, right? So it can be a little confusing. Why? Because observers have access to data, so they can pull this information whenever they need, right? So we're not pushing; we are pulling, right? So the views would pull the data, right? From the observers would pull the data from the model. All right, so how would it look if we were to do the push model? Well, it's coming up. We shall see it in a few moments. So this is their observable class from JDK. It is marked as deprecated, and it is deprecated, but it's not because the pattern itself is bad. It's, as you can guess, because it wasn't correctly implemented in the standard Java library to begin with. Right? So there's nothing wrong with the pattern, but the implementation of this pattern in Java is somewhat broken. It's broken in a way that doesn't really affect us. Right? So, for example, some of the certain aspects of these flaws only manifest themselves in a multi-threaded applications, which we're not talking about. Right? So we can totally use this as an observable interface. Right? Disregard the fact that it is deprecated. Right? It's not because there's something wrong with the pattern itself. Right? So see how this observable actually allows us to implement both the pull and the push model. How does that happen? Well, the update method, it takes this and the name. Okay? So the name would be the data that had changed, and this would be an instance of the model itself. And then it's up to the observable to decide whether it's going to be using this, an instance of the data model, or name the new data from the data model. So it can be either a push model or a pull model. All right, so that is pretty flexible. So if we want to implement a push model with an observable, then we have to make sure that our update, right, we only use the name, the new data, okay, that was pushed to the observable by the model. And we completely ignore the obj, right? So we only take the arg, the second argument of the update. Right, so that would be the view, okay, name observer in this case. All right, what about the, and we don't care about this first argument as we already discussed, right? So that's another view, right? Price observer. So again, two observers for the same model. What about the pool model? Again, same observer from the GDK. Same update with two arguments, but here we ignore the second argument, arg, and we take the first argument, which would be the model. Observable, right, is what is being observed, so it is our model, and here see how the observer, our price observer, or name observer, or whatever observer, is going to be extracting data from object. Right? So at first, of course, casts it to the proper type, and then it extracts the new data from the model. Right? Model here is object. All right. So again, that would be one of the views. Here is what the client might look like. Right? So this is the client that this is the client that creates two observers, name observer and price observer, and they are watching for the state of their name in the data model and the price that the data model will change. All right, so now the important words here were, well, this is our model, right? This is what stores the data, name and price. This is one view, name observer. This is another view, price observer. Right, so we have multiple views, and see how model is separated from the views. But we also have we also going to have some connecting tissue. We have to have some driver code that allows the views to work together with the model. Okay. Currently, they're just class definitions. Right, we don't have any code that creates an instance of the model, of the sale item. We don't have any code that would be creating name observer, price observer. So we have to have this driver code, and it is called controller. Right? So here it is. Here is the controller, okay? That creates the model sale item that creates our observers, and that kind of links them together. Right? So this observer pattern actually led to a more general pattern that is known as MVC, model view controller, and this is exactly what you will need to implement in your last homework assignment. So you have to take your graph ADT, and the data set is not going to be different. It's not going to be a Marvel universe anymore, but it's going to be another graph. And you have to structure code so that it implements the MVC pattern, which, as we just discussed, is a type of an observable pattern. So you have your model, your graph. You have multiple, or at least one, but maybe multiple views, and you have the controller that is responsible for, well, first interacting with their user, right? So all input output with the user, like taking their name of their node from which you want to build a path, taking the node to which you want to build a path. That would be the responsibility of the controller, right? And then basically connecting their model with the views, right? So if something, all right, changes, if there's some user action, then the controller would implement the change in the model, and that would in turn cause their notification of all observers. But of course, it's the job of the controller to tie their observers, the views, with the model, right? And this is not here, right? This is how the model is made aware of the observers who this model needs to call when data changes. How does data change? Again, the controller changes the data by working through the methods of the model that allow the model to modify its state. Right, so basically this is the MVC, right? Say Liven is the model, price observer, name observer are views, and client is the controller. All right, so that should be hopefully sufficient. We're going to go over more examples, but that should give you enough information to start working on your next homework. Once you go down to the current homework, then of course we will continue on Thursday. Have a great day, have a great night, and yeah.